Okay, welcome back, everybody. So this is the last lecture on complex analysis, which is great. Let me think. There's a couple of administrative things. We have a box to turn in homework in the ME front office. So now, please turn it into the box and not to me. You can also submit it, I think, online to the Canvas Dropbox thing, which some of you know about, and the TAs will get it electronically. I kind of prefer paper copies, but that's just me. I'm not grading them, though, so it doesn't really matter. There's no class on Monday. It's a university holiday, so don't come to class on Monday. I won't be here. I haven't decided if I'll make up the lecture with a video recorded lecture or not. So until you hear otherwise, there just won't be any class on Monday. I'm also not sure I want to have a second homework due 1 week from today. And I just wanted to gauge interest. How many of you would be crushed if you didn't have a second homework due next Friday? How many of you would be slightly crushed? Not a lot, just a little. It's okay if we don't have a homework next Friday? Okay, I think I'm going to cancel next Friday's homework, and I'll still keep the homeworks worth 60% of the grade. Because there's just not that much stuff I want to ask you on this homework, and I definitely don't want to write a homework today. All right, so we'll have a bigger homework in 2 weeks that'll cover kind of the last week of complex and also the first week of PDEs, which will start next week. All right, are there any questions or anything administrative since I won't see you for about 5 days? Anything at all? Nothing? Okay, so all that I'm going to do today is complex integrals. All right, we know how to do Cauchy integral formula. We know how to do Cauchy-Goursat. We know how to do surgery on contours. We know the ML bound. And so now I'm just going to show you a couple of examples of integrals that are neat that you can do by hand. The most important one, the only one that I actually have to show you today, is the inverse Laplace transform, because we're going to use that more later. And it's a beast. It has 3 pages, so we're going to do this one time today. But it's kind of interesting. We're going to learn a lot and get some good practice. And then I'm just going to keep doing complex integrals until the bell rings. And anything I don't get to will be in my notes online shortly. OK, good. So we're going to do the inverse Laplace transform. And just, I've already asked you how many of you know how to derive these or look them up from tables. But I just want to kind of crowdsource. Why do we care at all about inverse Laplace transforms or Laplace transforms in general? What are they good for? I'm stalling. I don't. What do we use Laplace transforms for? Sorry? Okay, so for solving differential equations. Why are Laplace transforms good for solving differential equations?
Algebraic.
Yeah, so any time derivative becomes just a power of my Laplace variable s. And so instead of a nth order differential equation, I get an nth order polynomial, which in principle should be easier to solve either by hand or numerically. So that's a great one. What's another reason we would solve things using Laplace transforms? Maybe let's stick with ODEs. How many control theorists are in the audience? Okay, so what would you use a Laplace transform representation for a differential equation in control theory?
Transfer function?
A transfer function, right? So if the Laplace transform takes me from the time domain into the frequency domain. And so if I have some physical system like a mass on a spring or a bath of fluid or a rubber band, it will tell me, this transfer function will tell me what the output of my system will look like if I give it a pure tone sinusoidal input. Okay, so the Laplace transform gives me frequency domain information, which is really, really useful. We're also going to find that it's extremely important when you solve partial differential equations of the parabolic type, so like heat equations, where you can solve the equation forward in time, but you can't solve it backward in time. Laplace transforms are going to be super important for that. Okay, so I gave you 3 big examples because I have 3 big pages of math. I think that's the least I can do. So let's write this down. Okay, so our Laplace transform, the forward Laplace transform, we're going to talk all about Laplace transforms later. So I'm just going to write down the formula for the inverse Laplace transform. If I have some function in the frequency domain, this could be my transfer function, or it could be the frequency domain solution of a PDE. This is just some function in terms of a Laplace variable s. S is a complex number. Then this is defined as this really funky integral, 1 over 2 pi I, integral from gamma minus I infinity to gamma plus I infinity of my function, e to the s t integrated with respect to s. This is just a definition. Triangle above an equal means I'm making stuff up. And there's a few conditions. So time is always positive, or at least non-negative. And gamma has to be greater than the real part of all poles of my function f. Poles are just another fancy word for singularities. They're divisions by 0 in the complex plane. Okay, but it's not that complicated. This is what I want. If I want to solve the inverse Laplace transform and find my time domain function, this is what I have to do. I have to compute this big integral. Okay, so I'm going to do a simple example that just kind of shows how we use Cauchy integral formula and ML bounds and all the stuff we've learned to actually solve these inverse Laplace transforms. So a specific example is the inverse Laplace transform with f of s equals 1 over s minus a. Okay, this is one of the most frequent frequency domain functions that we're going to deal with in systems, dynamics, control theory, all kinds of linear dynamics end up looking like this. This is also the solution to the simplest ODE x dot equals a times x. If I took the Laplace transform of this, I would get something like, Laplace of x dot is s times x hat. And so that equals a times x hat. And so if I collected all of this stuff, I would get x hat equals 1 over s minus a. Okay, so this is the transfer function for our simplest differential equation ever. We'll go way more into detail on this in a later time, so don't worry if you don't remember what the Laplace transform of a derivative is. We'll go through that later. But this is a really important transfer function, and so I want to motivate that we can actually do something useful by taking the inverse Laplace transform. So I want to know what is the solution in time for this transfer function. So I have to inverse Laplace transform this. Okay, we know the solution in time is x of t equals e to the a t x naught, but I want to be able to get that using my inverse Laplace transform function. Okay, because it's not always true that my function is so simple that I know its solution in the time domain anyway. Okay, so this thing that we're trying to solve is the Okay, so what I want is the Laplace transform inverse, the inverse Laplace transform of 1 over 1 minus 1 divided by s minus a is this thing, and I'm going to plug 1 over s minus a into f hat. So this is my big integral gamma minus I infinity gamma plus I infinity of e to the st divided by s minus a ds. What is this starting to look like? looks like a analytic function with a pole that I've inserted at A. Right? So this looks a lot like I can apply Cauchy integral formula. Okay, so this is what we want to solve. And I'm going to draw this contour in the complex plane and get some kind of geometric feeling for what we're actually doing. So this is my complex plane. And it doesn't matter where my pole is in the complex plane. Let's say it's a positive pole, so this is an unstable differential equation. Then my my contour here is going to be a contour in the vertical direction at some real valued location that's to the right of my pole. Right? Gamma has to be greater than the real part of my pole. So I'm going to draw this contour here, going kind of up forever. And that's what I want. I want this big integral over this red line. Okay? Now, what's a way that I can use Cauchy integral formula for a pole here and some integral with a big vertical segment? Sorry?
You can do a radius on it.
Yeah, so I could try to close this loop somehow. Okay, and the way I'm going to close it, this is kind of the classical way that most people do it because it's the simplest way, is I'm going to add these positive and negative segments here. I'm going to call this C plus and C minus. And then I'm going to have a big radius, which I'm going to call CR. Okay, so let's just do a little bit of definition. So this is a big circle of radius r. These points here are gamma plus IR and gamma minus IR. Okay? And the integral that I want is the vertical segment of this as I take the limit for r goes to infinity. Right? If I take this shape, this geometric D shape, and I blow it up to r equals infinity, then this vertical integral portion is my inverse Laplace transform. Okay? Good. So what is this big, so this shape, this D shape, is called Bromwich integral. Okay, not to be confused with the Bromwich integral. Any of you know what the Bromwich is? Most evil sandwich ever made. Wheat harvested from hell's half acre. Mayonnaise made from the eggs of deranged chickens. You never heard of the Bromwich? No? All right. So this is the Bromwich integral. Okay, and let's take a step back. What do we know about the integral of this function over this contour for any r? Sorry? We can apply Cauchy integral formula, which would be 2 pi I times my analytic function evaluated at my pole. Right, my pole here at A. So this big integral, let's say 1 over 2 pi I times my big contour integral, this whole Bromwich integral, of e to the s t over s minus a ds is equal to, okay, well, it's equal to the integral I want. Sorry, let me say that the limit as r goes to infinity of this thing is the integral I want, the inverse Laplace transform of 1 over s minus a, plus the integral around c plus the integral around c minus, plus the integral around c at radius r. Right? The big contour integral is equal to the thing I want, plus this segment, plus this segment, plus this segment. And this whole thing, all four of these integrals add up to what you just said, which is I take Cauchy integral formula and I get 2 pi I e to the at divided by 2 pi I. So this whole thing equals e to the at. Okay, any questions about that? I did the last step a little fast, so maybe if there's questions, this would be a good time to ask. Does that make sense? We had this integral we want, and I have no idea how to solve it, using classical calculus methods. So I cooked up some big contour integral around my single simple pole. I know what that integral equals because of Cauchy integral formula. And so then I can argue that that Cauchy integral portion, which is e to the at, is equal to the thing I want plus the other three segments. And what I'm going to argue is that as r goes to infinity, these three segments go to 0. So we need to show, we need these to go to 0 as r goes to infinity. That's what I'm going to spend the next 15 minutes doing, is showing that each of these terms goes to 0 as r goes to infinity. And if that's true, then my Laplace transform, my inverse Laplace transform is just e to the at. Right? Inverse Laplace transform plus 0 plus 0 plus 0 equals e to the at. Which is what we know it has to equal from basic differential equations. Okay, no questions? This is the important time to ask questions because we're going to go deeper. Yeah?
Why the contour has that vertical line right there again?
This one right here?
Yes.
So this vertical line is my starting point. You know in those books where you, it teaches you how to draw animals and you start with one big line and then you add the ears and the eyes and everything? This is the thing that I started with. This vertical line is the thing I care about. If I take the limit as r goes to infinity, this vertical line is the integral that I want, my inverse Laplace transform. So I'm starting with that vertical line. And I'm just trying to make any way possible in the complex plane to figure out what that vertical line equals.
Thank you.
Yep. Okay. There's an interesting question related to that. Hope this isn't confusing, but let's say that I had my pole and I had my vertical line. So I told you that it's useful to construct this contour here, this Bromwich integral. Why didn't I construct a contour going this way? Sorry, both of you said something. You said because it equals 0. So this contour integral equals 0. Why? No pole inside. The function's analytic. And you said?
It will not include pole.
Yeah, so there's no pole inside, so this integral is equal to 0. But that just means that this big positive contour integral equals this vertical contour integral negative, and it doesn't really help us. We don't know any more than we did before. So I'm just trying to think kind of rationally. So we really want to be enclosing this pole because it says something very specific about this integral, and I can actually argue that these parts are negative. Why do you think I can argue that this big contour is negative? Sorry, not negative, I mean 0. Why does this go to 0 as r goes to infinity? And why does this not? This is the crux of my entire argument, so I figure we should just start there.
Can't you do an ML bounds on the outer one and you get the limit as r goes to infinity, and that would say that would...
So that would be a really good idea. I tried it and it didn't work. Why do you think that the ML bound might work on this though? Because this length is infinite. It's pi r and r is going to infinity. So why would the function times L, why would m times L still go to 0?
So that integral, the area under the curve will be a function of the inverse of the radius. But we're only at a power 1, so it wouldn't work.
So this isn't true for any function that I'm inverting. This is true for inverse Laplace transforms. And they have this e to the st. Okay? So I basically have something like, e to the st over s minus a. And what does e to the st look like for positive and negative real parts of s? Yeah, so if the real part of s, if s is positive real part, that blows up. It's huge. If s has a negative real part, this is really small. And if I take r goes to infinity, it has a really, really negative real part most of the time. Okay? So that's the basic idea. This contour we can expect to be relatively small because this thing just gets small for negative real part s, and t is always positive. And if I had positive real part s, everything would blow up. So this is not equal to 0. It's like a nasty positive integral. That's the intuition behind what we're doing. Okay? I'm going to erase this. Okay, so I told you couldn't use ML bounds for the big radial portion, but you can certainly use it for C plus and C minus, because the L never changes. The length of these is always gamma, so it's always small. And I claim that my function part's going to get smaller, is going to go to 0. Okay, good. So let's do this. Okay, so we're going to solve the C plus and the C minus parts using ML bound. Okay, and I just told you the length never changes. So for C plus and C minus, we have, they're just gamma long. L never changes. L is always equal to gamma. Just a number. Okay? So this is true regardless of r going to infinity. Okay, so we're going to take this, let's just do integral of C plus of e to the st divided by s minus a ds. Okay, so what do I need to do to this function to apply ML bound? I basically need to show that this function goes to 0 on that curve. Right? I need to show that this function is bounded by another function that goes to 0 as r goes to infinity. Okay, so I'm going to... this actually is an easy integral for me to write out. Usually I write these contours C, and that's a way of me avoiding actually using coordinates. But I can actually write this out in coordinates because it's just moving along the real axis direction. So this is the integral from gamma plus IR to IR. So gamma plus IR to IR of e to the st over s minus a ds. And that is the same as integrating just in dx from gamma to 0. So I'm integrating from gamma to 0 in dx. And what I'm integrating is e to the x plus IR t divided by x plus IR minus a. I just plugged in s equals x plus IR on C plus. Right? On this curve, my complex variable s is restricted to be some real part plus IR. The imaginary part's always IR. Okay, so I can take my contour integral, just my line integral, and I can literally write it as a line integral in dx. If I say anything wrong, please shout, interrupt. Okay, and this thing is going to be less than or equal to ML. And so we need an M. So basically I want to take this function and bound it. Okay. Now how do we do that? So m is going to be the maximum of this function for x between 0 and gamma. So it's the max over all x between 0 and gamma of this function, e to the x plus I r t divided by x plus I r minus a. I don't want the absolute value because I don't care if it's positive, negative, or has some complex phase angle. Don't care at all. So m is going to be the maximum of this function over the entire possible range of x from 0 to gamma. And I'm going to show that this has to go to 0 as r goes to infinity. The maximum absolute value of this function shrinks to 0 as r goes to infinity. That's what we're showing. Okay, and so this thing is less than or equal to, actually pretty sure it's just equal to e to the gamma t over r. So the worst case numerator I can possibly build, the biggest numerator, is has x equal to positive gamma. Right, like e to the 2 is bigger than e to the 0. So e to the positive gamma is going to be bigger than e to the 0. So plugging in gamma for x is going to have to make the biggest numerator. And similarly, the smallest denominator is when x is equal to a, then this would be r. So this thing is at least less than or equal to this. You can convince yourself that this is true. Gamma and t are positive. Gamma is a constant. So this goes to 0 as r goes to infinity. I didn't convince you terribly compellingly how to go from here to here, but it's not that complicated. Like e to the real part plus imaginary part, its magnitude is never going to be larger than e to the gamma t. That's the biggest this thing's real part can ever be, is e to the gamma t. This bottom part looks a lot like 1 over r. And as r gets huge, this r is going to dwarf either of these two terms. It doesn't really matter what I plug in there. This thing is basically never going to be bigger than e to the gamma t divided by r. Okay? That goes to 0 as r goes to infinity. And so I have m times L equals 0. And so this c plus integral has to be equal to 0. So integral of c plus equals 0. Similarly, integral of c minus equals 0. It's the exact same thing, but with a couple of minus signs. Okay? Are there some questions about what went on here? Does this still bother people? I feel like this is bothering everyone, myself included.
The r's constant.
Okay, yeah, sorry, I skipped a lot of steps. So e to the x plus I r t equals e to the xt e to the I r t. T is a positive number. It's time, right? It's not complex. It's not negative. It's positive real number, time. So this is the real part. The real part. This is the imaginary part. And so this equals e to the xt times cos I rt plus I sine rt. Okay? Now, the length of this thing, the magnitude, the radius of this complex number is this. This is the magnitude. This is just the phase. This can never increase or decrease my magnitude. Okay? So the length of this thing, the raw length or size of this function is given by e to the xt. Okay? And how do I make e to the xt bigger for positive x between 0 and gamma? I use the biggest possible value of x on my range, which is gamma. So e to the gamma t is the largest this is ever going to be. E to the 0t is just radius 1. That's the smallest it's ever going to be. So this function is largest, it has the biggest numerator, e to the gamma t, when x is equal to gamma. So sorry, I skipped like 2 equal signs. That's bad. I can skip 1 equal sign, but not 2. Does that make sense now? And the denominator, this part always confuses me, but basically x is not going to be bigger than gamma, a is definitely smaller than gamma, and r is going to infinity. So this thing is divided by infinity. Okay? All right, so C plus and C minus are 0. But that was, unfortunately, the easy part. As I told you, the CR curve, you can't actually use ML bound on this. You have to use something that's slightly better than the ML bound. It's called the Jordan lemma, which means it's harder than the ML bound because some guy's name is on it. They don't put your name on things. I guess they put Euler's name on this. That was pretty simple. Yeah?
When both of these integrals are 0, so why do we need them? So why do we just put them, we can just write a circle without...
Oh, yeah, so great question. So why didn't I just have a big circle here, like that?
Yeah.
That's just a much, much, much harder integral. Like, this function is weird. It's z minus gamma equals r e to the I theta, and it's just a lot harder to solve. Like, this is a nice constant radius with respect to the origin, 0, but this dash curve is not. It's like a weird function with respect to the coordinate system we're in, which is centered at 0.
So even if it's circled still...
It's still a pain. Try it out. Try to evaluate this integral, and it'll be almost impossible because you won't be able to use the Jordan lemma. We're going to rely on the fact that this entire curve has negative real part. Okay, but this dashed semicircle does not have its entire curve have negative real part. It has these parts here, and so that's why I like to kind of solve them separately using ML bound, even though they're finite and positive. They're the length is finite and positive, that term goes to 0 as r goes to infinity. So I handle those separately. This is really the right way to do it. If you try to do it a different way, it becomes harder, believe it or not. Okay, does everyone feel okay about, yeah?
Is there a reason why we can't basically have it C positive, just the negative integral of C minus, like we did with the epsilons, with 2 poles?
Okay, it's a good question. So this one is C plus. Let's see if we can write down C minus. It's not obvious to me that C minus is actually minus of C plus. They both equal 0, so obviously they are equal and opposite and the same all at once. But it's not clear to me that that negative curve actually cancels this out. So how would we write that out? So C minus is the integral from 0 to gamma, because we're going from left to right, of the same exact function, except now I have e to the x minus IRT, because I'm at minus IR, divided by x minus IR minus a dx. So this is C minus. It's a really good question. I've never thought about this before.
Equals -0.
This definitely equals -0. But let's say that I didn't take the limit as r goes to infinity. Like, can I actually cancel these out for finite r's? I'm almost sure you can't, because I'm pretty sure that this thing does not equal 0, and so these have to add up to something that cancels that out. So I'm pretty sure that they don't cancel. I'm just trying to show it easily. So the way you would do this is essentially some complex number e to the x minus IR t divided by some real part x minus a minus IR. And what I would do is I multiply top and bottom by a complex conjugate transpose. So I had just a complex function divided by a real number. And I would do that to this function and to this function. And I'm pretty sure you can show that they don't cancel out. So that's how you would do it. I think it would take a long time to actually show that they don't cancel, but I'm certain they don't cancel because I know that this curve is not equal to 0 until I take r to infinity. And so these components have to add up to something finite that cancels. No, they might equal. They might cancel. I don't know. You, try it out. Tell me if they cancel or not. I don't think they do. Or else I just wasted a lot of your time. Okay, so the last one that we need to solve is integral of CR. And this integral is a little harder, so you can try to do the ML bound, and you'll find that you run into a problem. The ML bound is not, it's just an upper bound. It's not the tightest bound possible, so it doesn't always work. There's lots of cases where the function really does go to 0. The integral does go to 0, but the ML bound doesn't prove it for me. Okay, it's just an upper bound. So all right, the best way to do this is just to jump in. So now we're going to do the integral of the big radius portion. We're going to take that radius to infinity. And so ML doesn't work. And so we're going to try polar coordinates. Now, if I had all the time in the world, I'd show you that ML bound doesn't work. But you can try it out. And if we just tried to do ML bound, we'd run into an obstacle. It wouldn't work. Okay, so we're going to try polar coordinates. We're going to say x equals minus r cos theta, and y equals r sine theta. And we're going to draw this picture where our red curve here, our red curve is like this. And my coordinate system theta, this is a little different than what we normally define theta from the positive real. Here I'm defining theta from the negative real, just because it makes my math easier. You could do it from positive real, you just get a bunch more negatives and weird stuff happening. So I'm counting kind of up from -1. Okay, so I'm going to take my integral, and I'm going to take the numerator and the denominator, and I'm going to try to get as tight of a bound as I possibly can on both of those terms. Okay? On this red curve here. So first I'm going to take e to the st, and the absolute value of that is going to be the real part of s times t. So that's equal to e to the minus rt cos theta, if I use these coordinates, right? This is just the real part, xt. This is what we wrote down when I skipped all of those steps. This is, the norm, the length of this e to the st is given by e to the xt, and I'm using these coordinates for x. Pretty straightforward. Okay, and now I need a bound for s minus a, the denominator, and this is kind of a tricky one. So I'm going to plug in my coordinates here. So I have minus r cos theta for the real part, minus a. So this is my real part. And then I'm also going to have plus I times r sine theta. I literally just took my polar coordinate representation and I plugged it into s minus a. And I'm writing down the real and the imaginary part. Okay. So the length of this, now I'm just going to use Pythagorean theorem. The length of this is the square root of this squared plus this squared. Okay, so that's what? R cos theta plus a squared plus r squared sine theta squared square root. Okay, blah, blah, blah. I'm going to skip. You can expand this out, collect terms, solve for some stuff. And basically what you can find, this is r squared plus 2ar cos theta plus a squared. And that's bigger than or equal to the length of r minus a. This is the length of r. It's going to be really, really terribly boring if I try to prove to you why this is true, but you can draw a picture. Like just draw a picture in polar coordinates of s minus a, and you can convince yourself that it really is larger than this at this step. Okay? Okay, good. So I have a bound on the numerator. Well, I actually know exactly what the length of the numerator is, and I have a bound on the denominator. My denominator is larger than that in magnitude. Okay, so we have our contour integral of e to the st divided by s minus a ds is less than or equal to integral minus pi over 2 to pi over 2. I should tell you that this is pi over 2, and this is theta equals minus pi over 2. Right, in this coordinate system, positive pi over 2, negative pi over 2 for theta. So I'm integrating from theta equals negative pi over 2 to pi over 2 of this thing divided by this thing. That's e to the minus r t cos theta divided by r minus a norm. And I'm integrating that in polar coordinates, so I get an r d theta. Okay, and I'm integrating this purely with respect to theta because my r is constant. And so I'm going to just pop all the r stuff out. So this equals r divided by norm of r minus a times integral minus pi over 2 to pi over 2 e to the minus rt cos theta d theta. Okay, we're almost done. Except I don't know how to integrate this. Does anyone know how to integrate this? There's one more trick. It's terrible, because I don't know how to integrate this. I just don't have, I'd have to do another terrible contour integral probably. So what we're going to use is we're going to use a final trick. So kind of final trick is that cos of theta is always greater than or equal to 1 minus 2 theta divided by pi on the interval 0 to pi over 2. I don't know why this is true. I found this on the internet. This is true. Cos of theta is always bigger than this. You could prove this if you wanted to, but just, this is a trick. This is the last trick I'm going to use, okay? You have to use, unfortunately, a lot of these things for really hard integrals. So I'm basically going to take this integral, and I'm going to say that it's less than or equal to, sorry, it's greater than or equal to, I'm just going to plug in 1 minus 2 theta over pi for cos of theta. Okay? So, so my complex contour integral around this curve CR is less than or equal to r over r minus a magnitude integral minus pi over 2 to pi over 2 of e to the r t 2 theta over pi minus 1. And I can actually integrate this thing with respect to theta. Okay, so that equals r over r minus a. So if I integrate this with respect to theta, then I have some big constant 2rt over pi. That's my constant, so I get times 1 over 2rt over pi, or maybe my pi can go up here. E to the rt 2 theta over pi minus 1, evaluated at minus pi over 2 to pi over 2. Okay, this thing ends up being something like sorry, this is bad. Okay, so you can go through all of this and you find that what you end up getting is this r and this r cancel. We have pi over magnitude of r minus a times t, and this thing evaluates out to 1 minus e to the minus r t. It's a lot of calculus. This isn't a calculus class. So this thing evaluates out to this, and I cancel out my 2. And finally, we see that this term, as r goes to infinity, this looks like 1 as r goes to infinity. This term looks like 1 over r as r goes to infinity. So this whole thing equals 0 as r goes to infinity. Okay, now this is a terrible algebraic and calculus-based proof. You have to do all this messy garbage to actually show that it's equal to 0. But the basic intuition is that on this portion of the curve, the real part of e to the st is always, the real part of st is always negative. So e to the st is small. And as I make this radius larger, e to the st gets smaller, a lot smaller. And it gets smaller faster than this length. So this is basically like a fancy, refined version of the ML bound. Okay, we still used a bunch of like boundings of the numerator and the denominator and all of this stuff to show that this is equal to 0. Okay, I want to leave that board. So what we've done is we've taken our inverse Laplace transform, which is this big single segment infinite length integral. We've connected this around the single simple pole at s equals a to use Cauchy integral formula. So we know that that whole thing equals e to the at. And then we showed that all other segments, except for the one we care about, all integrate to 0 as my radius goes to infinity. Okay? That was a lot of work that took the entire class just to get to the fact that my inverse Laplace transform of probably the simplest transfer function ever equals e to the at, the solution of the simplest differential equation ever. Okay? So I'm not recommending that you actually use contour integrals to solve these problems and not use a lookup table, but you really, really, really should know that you actually can do these things by hand if you have to. And when you plug this into Mathematica, it's actually doing all of these tricks like in its computer brain very, very quickly, but it knows all of these tricks and it's applying them. That's actually how it's solving these things. It's using Cauchy integral formula. Okay? That's all that I want to tell you. That's all that I have time to tell you. In the course notes, which I'm going to upload sometime early this afternoon, there are 2 other examples of complex integrals, and I just want you to look them over and get a feeling for them. Because they are the kinds of things I would ask on midterms or finals or quals. So there's 2 extra contour integrals in my notes. They are fair game. You might as well consider that like the makeup lecture for Monday. Okay? That's all. Have a great weekend. I'll see you on Wednesday.